The host has started broadcasting the meeting on custom live streaming service.
A very good evening to all of you present here. A very hearty welcome to all of you to today's talk. So today's talk is on coloring of graph and some bounds on. The speaker for today's talk is Dr. Shuchita Goyal, ma'am. A very warm welcome to you, ma'am. So before we begin the talk, I would like to give a brief introduction about ma'am. Dr. Shuchita Goyal is a mathematician with a keen interest in topology and combinatorics. Currently, she is serving as an assistant professor at Krea University. She has earned her PhD from the prestigious university, that is IIT Bombay, with approximately 4.5 years of valuable professional experience. She has been associated with renowned institutions such as IIT Bombay, IIT Kanpur, Chennai Mathematical Institute, etc. Her diverse roles likely include teaching, given her engagement with these esteemed institutions. Besides this, one of the, I guess, proud moment to all of us is ma'am is an MTTS alumni. She was a participant of MTTS O level in the year 2008 and MTTS level 1 in the year 2009. A very warm welcome to you, ma'am. Today she'll be presenting a talk on graph coloring and some bounds on it. This presentation will delve you into fascinating topics like graph coloring, chromatic number, and Brook's theorem. Before we move into the presentation, I would like to give few uh, kind of rules or few kind of advices to the audience that kindly don't unmute yourself until you're asked to. If you have any query, kindly make use of the raise hand button that is utilized given in the Zoom. Over to you, ma'am.
Thank you, Bhumika. Good evening, everyone. So, the topic has already been introduced. Let me begin with the presentation then. I'll switch off this video and start the sharing. Okay, so as the topic says, it's about graph coloring and we'll see some bounds on it. First of all, what a graph is and why one should care about its coloring, and then why some bounds. All of those things we'll see today. So let me start first of all with what a graph is. Is my screen clearly visible?
Yes.
Yes, ma'am.
Okay. So for a graph, suppose every oops. If let's say I talk about two cities, city A and city B, then there is supposedly a road connecting the two cities. Let me draw this road. Similarly, I can have another city, let's say C, and there is a road from B to C. For sure, road could be in all different sort of shapes, but the shape of the road is immaterial to me right now. So I'm just drawing a simple line. Okay. So something like this, if let's say I call these things here as my vertices, the cities, okay, and the connection between them I call as the roads or the edges. Then what I have effectively done is I have defined for myself a graph, which means graph is nothing let's say graph G, it's a collection of two pairs, VG, which we call the vertices of the graph, and EG, called the edges of the graph. Okay, so the vertices are these red ones, which we have done upstairs, and edges are the lines which we have drawn between these vertices. So, if I have such a graph, there are many ways I can, take any real life example and construct a graph out of it. So, for example, you saw something in the background of my image on the front page. Any guesses what this is? At least if I show this much part. Any guesses? So this is actually
World
map of the world. Yes. Where I have hidden the country names. So only the country boundaries are shown. And the boundaries as it is do not really play any role because I have colored the inside of them. So this color you see here, all of this light reddish thing is denoting India, right? All of this piece is my Russia. So I have color coded the entire map. And one beautiful thing is this entire thing can be translated in the definition of a graph. And then, of course, we can talk about the graph coloring as well. So how that works is this way. So let's say if you have some countries, C1, C2, C3, etc. And then you put countries as the vertices, all right? And put an edge between them if they share a boundary. Okay, so if this is, let's say, my India and this is Nepal, I will have an edge. Whereas if, let's say, C3 is my UK, this edge will not be present, right? So this way, entire world map can be translated into a graph. So this is all about the definition of a graph. Once I have understood graph, I can talk about better things. And they are how I can color a graph. Here you see the graph, two things. One is vertex set and another one is edge set, right? So I have a chance to either color vertices or edges. When you color vertices, it's called a vertex coloring. When you color edges, it's called an edge coloring. For today's talk, we are going to talk about the vertex colorings. Okay. So what this is suppose I take a function from the vertex set of graph to some finite set. Okay. And now, what this function is supposed to do? Vertices of the graph which are adjacent. So V prime belonging to H set. If this happens, then their value should be different. Okay. If you want, you can just consider this as some 1 to k for some k. It is the set. So With this notation, what we really are saying is that every vertex should be given some number, and two adjacent vertices, meaning vertices which are connected by an edge, they should go to different numbers. So the numbers here, these numbers, okay, maybe not a very good choice. These numbers are actually my colors. So S considered as colors. Yeah. So for example, if let's say I would have taken this graph with three vertices. Okay. Vertex A, vertex B, vertex C. Well, then C is adjacent to A as well as B. Therefore, I will have to pick a color which is different from both of these for the vertex C. So let's say I pick this color. This way I have defined a function f from the vertex set A, B, C to 1, 2, 3, where all three vertices have gone to three different numbers. Such a coloring is called a proper coloring. Okay. One could just define without asking the condition that, adjacent vertices have to go to different colors. You could just define a function in which, let's say, you give one color to all the vertices of the graph. That's also coloring, but that's not a proper coloring. Proper coloring is when adjacent vertices go to different colors. So this is a way of defining a coloring. Now, condition is, well, here I had certainly three vertices and all of them needed different color. But for example, so let's say E1, this is E2. If let's say I would have taken this example, 1, 2, or rather A, B, C. In this case, I can give this as red. Okay. Then since B is adjacent to A, it has to get a different shade. And now C adjacent to B, I can give it again red or a different color, right? So you can either give it a different color or you can give it a color which you have previously used and available. So chromatic number of a graph is the least number such that there is a function defined from the vertex set to that number. So you take a graph, okay, and if n is the smallest positive integer such that there exists a function f from the vertex set of G do this, which is a proper coloring, then the number n is called the chromatic number and it is denoted by chi of that graph. Okay. So this is my chromatic number. So again, going back to what I had shown earlier, if you see this graph map, or rather the graph which is corresponding to this particular world map, a famous theorem is the four color theorem, which says that no matter how many countries are there and how they share the boundary, if you're looking at the world map, then at the most four colors are sufficient to color all the countries, so that no two adjacent countries will have the same color. Because if two adjacent countries get the same color, as you can see here, if let's say this and this got the same color, then this boundary will not be visible, right? Therefore, the adjacent countries we would want to give different color. And adjacent countries giving different color is same as my definition of giving a proper coloring to the associated graph for the world map, right? So all of this boils down to the fact that world map can be colored using four colors. That's it. Such that no adjacent countries get the same color. This is a famous four color theorem, and it is not just for the world map, it is actually a much more generalized statement, and it is about the planar graphs. Some graph is planar if you can draw it on plane on R2 so that no edges intersect each other. Okay, so something like this is not allowed. So if let's say this was your graph, you rather than drawing it this way, you would take this edge like this, but then this can come this way, right? So this is a planar drawing. While this is not of the same graph. So if a graph exhibit a planar drawing, then the graph is called planar, and every planar graph can be colored by using at most four colors, which means for any planar graph, the chromatic number is at most 4. But this is not our main point of attention. This is just to motivate you why people care about graph representation of situations and then colorings, and why things get interesting and intimidating. So once I have understood the world map and its coloring, now I can talk about some more theory related things for the graph. First being independent set. Okay, so if let's say I just have vertices and there is no edge connecting any two of them, The definition of independent set comes from exactly this point, that the is my internet fluctuating, Soumya?
No, I think we can hear you.
Okay, I just got a screen message that it's unstable.
No, we can hear you.
Okay, great. So if let's say I look at these vertices and there is no edge among any of these, then I say it's a independent set. So what independent set means is that, so some subset, let's say A of the vertex set, such that for every V and W, if you would have chosen from A, VW is not an edge. In such a case, A is an independent set. Okay. So if, let's say I take my old example of this, A, B, and C. Tell me one independent set, which means I want to find some subset of a vertex set such that there are no edges between those vertices. So if let's say I take A, can I put B? No, it's adjacent to A. Can I put C? No, again same problem. So independent set is just this. Any other independent set? Sure. By symmetry, I know B and singleton C are also independent sets. Yeah, this is it. But if I take again the old example, which was this, which looks like a path graph, because it's like a path, then if let's say I would start with A1 and put A in it, can I put B? No. But can I put C? Sure, because C is not adjacent to A. So if I would look at just the vertices A and C, there won't be any edge between them, right? This is not there. Only A, B, and BC are there. So AC as it is stands out just as two vertices, no edge. So that's an independent set. A2 consists of just B. Because as soon as I put B, I cannot put A, I cannot put C either. Yeah? So this one would have corresponded to just this. Okay. So independent sets are those subsets which are giving you graphs without any edges. In contrast, there is something called a clique or a complete graph. Let me first define clique. So this again is a subset of the vertex set such that now if you choose any two vertices from this set, the VW has to be an edge. See, it is completely in contrast with what I have seen earlier. Here I demanded VW should not be an edge, and now I'm demanding VW should be an edge. Okay. So if you have edge between every two vertices of the set, you say it's a clique. Hello? Am I audible?
Yeah, now we can hear you. Yeah,
Oh,
yeah.
yeah, somebody muted me in between.
Oh, okay. Sorry.
Yeah,
Yeah, please continue.
no problem. Yeah, so should I repeat the click set?
No, click definition was clear. Yeah.
Yeah, okay. So A is a click if every pair of vertices of A has an edge between it. Okay. And just to see again as example, if let's say I have this ABC, then if I choose any singleton set by default, vacancy, it's a click because there are no two vertices in it. If I would have chosen, let's say AB, is that a click? Sure, because AB share an edge. Similarly, AC, BC, those will be clicks. Let me not write those. A3 and A4, you can fill those. A5 given by all the three vertices is also a click, which means what I have drawn here, this graph in itself is a click. And when the graph itself is a click, you say that it's a complete graph. Okay. So this complete graph has three vertices. So I will call it K3. Okay. And similarly, I would have Kn as complete graph on n vertices. All right. So this is good. Now, you might notice that when I was talking about independent set, every independent set, I mean, given any graph, you can have independent sets of varying cardinality. So, is there any concept about fixing a number about a graph in terms of its independent set or a clique set? Yes. Since I know that if you take any singleton point, it's an independent set. And if you take any singleton point, it's a clique set as well. So it makes more sense to say what is the maximum size of such a set you can find in a graph. And these are called the independence number and the clique number. Okay, this is size of the largest independent set. And this one is size of the largest clique set. Independent set, remember, was nothing at all in terms of vertices, in terms of edges. And clique meant everything was present. See this? VW belongs to the edge set for every V and W. So this one is omega of g. Because if you look at the Greek alphabet, it starts from alpha being its first letter and omega being its last letter. So alpha means almost empty. You just started, you only have vertices, no edges, and omega means last, meaning you have all the things now. All the edges are present, vertices were anyway present. So these two numbers of a graph are quite important, and they give many relations in respect to the chromatic number which we have seen earlier. So let's now move towards those relations. First one is that the chromatic number of any graph is at least as much as the click number of that graph or click size. It's quite easy to see how this one follows. See, if I have a click in a graph, click means all the vertices are adjacent to all other, which means every vertex of the click has to be given a different color. So if there is a click of this much size, these many colors have to be given to just that much subgraph of the graph. And then there could be some extra portion outside which could need more colors. Therefore, Kaiji has to be at least as much as the click number. Second bound is the chromatic number is at least as large as cardinality of the vertex set divided by the independence number. Why this holds? If you see the number of the vertices that appear in any independent set, they can be given the same color, right? Let's come back to the example. You see here, A and C form an independent set. And therefore, A and C could be given the same color red. This one red as well as this one red. Because they together form an independent set. So, since every independent set works as one color class, your chromatic number has to be at least this much. But one thing is noticeworthy here, that if I am working with, let's say, Kn, then the chromatic number of Kn is exactly equal to the click size. Kn meaning complete graph on n vertices. And this is the number of click size, which means this is again n. And chromatic number of Kn is n. We just said that every vertex of the complete graph has to be given a different color because every two different vertices are adjacent. So this is true, which means this inequality becomes equality in case of Kn. If I look at this, alpha G, largest independent set that I can find in my complete graph, is just a singleton. Because once I would have put one vertex, as soon as another vertex tries to come into the set, it's going to be adjacent to it because it's complete. Because it's a complete graph, therefore I cannot put this vertex, which means alpha G is just the singleton point, or rather one, right? And Vg for Kn is going to be n, which means chi of Kn is n. So this is also equality. So when it is Kn, both of these bounds are giving you strict bound. However, these bounds are not great because, at least for this, it is quite easy to see that I can have a very small click size and still the chromatic number can be really huge. One such construction is through the Mieselski's graph. So suppose I start with the graph G. Okay. So this graph is going to have a vertex set and an edge set. From this, I will do some box business here. And the output is going to be M of G, which is going to be the Mieselski graph on G. What it does is this. The vertex set of MG is nothing but you repeat vertex set of G, disjoint union vertex set of G. So let's say every vertex which is labeled 1 here comes with a 1 prime here. And then at the end, you put a vertex X. And now edges are as follows. So let me just try to call this as the first copy of G and this as the second copy of G. So edges of G, or rather, how should I put it? Okay. Let me put it this way. So when I put this, I am trying to say that it's coming from the original copy. Okay, disjoint union, all of these, when it is coming from the same other copy, disjoint union, now the cross edges, which is that you take this from the lower and this from the top. Sorry, the second copy, if G1 and the corresponding H1 are in the original copy. Disjoint, the X which you have added, this is adjacent to everything in the second copy. So very simply, if I want to see this, let's say I start with a very small graph, let's say just K2. Okay, so this is my original graph. And then I will have this. Uh-oh, I don't want to add these. Yeah, I don't want these. So this was A1, B1, and correspondingly I have an A2 here and a B2 here. And now this condition says that bottom one be adjacent to the top one if the corresponding if G1 H1 is an edge. So then since A1 B1 is an edge, I will put A1 B2 as an edge. Similarly, since A1 B1 is an edge, A2 B1 is also going to be an edge. So if you just want to see this piece are given by these edges. Okay. And then at the end, let's say put a green color. These edges are going to come by this X. So if I just straighten it out, this is nothing but an X, A2, B2, A1, B1, and this. And this looks like a 5 cycle because it has 5 edges and it closes up. So if I would have given, let's say, color 1 to this, then this has to be given color 2, then this can be given color 1, then this color 2, but now I cannot give color 1 because this is adjacent here. So I have to choose a third color, which means the chromatic number, so this is one second. Sorry. Free. Which means start this graph.
Yes, ma'am. Now you are audible.
Okay. Now we talk about disjoint union of graphs.
Yes, ma'am. Actually, Sachidanand sir has a question. He has raised his hand.
Yeah, so sorry. Basically, I'm traveling, so there will be some noise. So, if you go to the bound or the inequality that you have told, regarding the chromatic number and the click number. Yeah. So basically, you told that for Kn, it's an equality. But like, are there any other condition on
Yes.
G where we can expect some equality? For example, in the path graph also, if you see in
Yeah, I'll
3.
come back to.
Okay.
Mm-hmm.
Yeah. Yeah, you can go ahead because you told that you will be saying this. So yeah.
Ma'am, you are muted. Yeah, now you are audible.
So stop disjoint union. So I will say that. Okay.
Yeah, Shuchita, your audio was breaking. Can you repeat?
I'm saying to Sachidanand that I'll return to his question in a while. That exactly is the later 10 minutes of our talk.
Sure. Okay. Please continue.
Okay. And talking about the disjoint union of graphs, if I take two graphs, I define the disjoint union of graphs by taking the vertex set to be the disjoint union and edge set also to be the disjoint union. Nothing fancy. So, sorry. So one can expect in such a case just the one whichever sort of has an upper hand. So you look at the chromatic number of both the graphs, and whichever has a higher one will win the race and give the chromatic number of the disjoint union of these graphs. Another construction where this kind of a result holds that. So this construction is about the disjoint union. There is one more construction where the chromatic number of the resultant graph turns out to be max of the chromatic number of individual graphs. So we just see that construction next, and then I'll be a bit quicker. And this is called Cartesian product of graphs. There are many different kind of products on the category on the graphs. So one has to be careful which product we are dealing with. In today's talk, I'm talking about Cartesian product. There is a categorical product, there is a strong product. But right now we only deal with the Cartesian product. What you do here is that given two graphs, the vertex set, you just take the Cartesian product of the vertices of both the sets, and in the edge set, you say some GH G prime H prime. This is going to be, collect those pairs from this. By the way, I did not say at any point in my talk, but I'm always dealing with the undirected graphs. Okay. So the chromatic number, etc., all that I've defined is for the undirected graphs, and I am assuming my graphs do not have loops. No vertex is adjacent to itself, because then I cannot in any way give different color to the same vertex. Okay, it's redundancy. So all my graphs are without loops. And since multiple edges do not play any role when you're dealing with the chromatic number, I assume that given any pair of vertices, there is at most one edge. So I'm avoiding the multiple edges as well. So given any pair from the vertex square, there will be an edge in this new graph either if the first component is same and the second component is an edge in the second graph, or the first components form an edge along with second component being the same. Okay. So as an example, I don't know, E6 maybe? I don't remember. So if let's say I take a path graph on 3 vertices and a path graph on 2 vertices, then I am first of all going to have these as my vertices for the vertex set in the Cartesian product of the graphs. Moreover, since this vertex is going to be equal in all of these, I just follow the adjacency of the horizontal graph. Similarly, for this, if I follow, I'm going to get this. Now, I have to take the other direction as well, which means if I look at this, then I have to follow this adjacency, which means I'm going to put this edge. Similarly, for this, I'm going to put this edge, and for this, I'm going to put this edge. So this way, what I've constructed is a grid graph. Of the size 2 cross 3, 2 vertices by 3 vertices. But what is more important is that this was proved independently by Wissing in 63 and Ebert in 64 that chromatic number of Cartesian product of graphs is equal to maximum of the individual chromatic numbers. Okay. Proof, not very hard to see. Now when people have proved it and we have it at our hand. So you see, G is definitely a subgraph of G Cartesian H, right? If you look at this particular graph, it is sitting as a subgraph in any of the vertical pieces. Or if you look at this, it's going to give you the horizontal graph copies, which means both of these graphs, the original graphs, appear in the Cartesian product. So the chromatic number of G product H is at least this much. To see the other way around, what I will have to do is I have to find a coloring which is max of this and should be sufficient to color this particular graph. To do this, what do I do is, let's say K is this number. Let me just put this here itself and save some time. Okay, and now let G is a color function from G to chi G. Okay, let me put this in bracket so that it denotes a set, and H be an chi H coloring of the graph H. Using these, excuse me, I can define F from the Cartesian product to K by sending any UV to GU plus HV modulo K. So modulo K just to make sure that it lands back within the K. But now, if let's say I would have, so I have given some function. Okay, all that I want to do now is that, say if I have UV which is adjacent to some other vertex U prime V prime in my graph G Cartesian H, then I want to claim that their F values are different, right? Now, see what can happen. If UV is adjacent to U prime V prime, by definition of the Cartesian product, either U is equal to U prime and V prime is an edge, or the other way around. So if I look at the case 1, U is equal to U prime, this would mean that G of U is equal to G of U prime, right? And V is adjacent to V prime, which means H of V has to be distinct from H of V prime. Now, when you add these numbers, what are you going to get? F of UV is G of U plus H of V, but this is same as G of U prime plus H of V, but this is not equal to G of U prime plus H of V prime, which is the F of U prime V prime. So F of UV is different from F of U prime V prime, which means F is a proper coloring. Same logic applies if U prime was an edge and V was equal to V prime. And this ends the proof. Now, how do you actually color a graph? This is the kind of only interesting thing left to talk about, or rather the gist. One easiest way, naively, if I give you a graph, how you would start coloring it? You will give one color to each vertex, which would give you that chromatic number is less than equal to the cardinality of vertex set. Again, this is strict, or rather this is strong. I mean, this is equality only if G is equal to Kn and no other time. If and only if G is Kn. This holds as equality. Otherwise, it's always less than the full set. Any better approach available? Yes. And that's where the greedy algorithm comes into the picture. So you don't start painting the vertices as you like, but you paint them wisely. And this tells you that what you do, first of all, order your vertices. Okay. Give some labeling to each and every vertex of your vertex set. Call some vertex as first, second, third, and so on, the last. In step 2, color V1 with, let's say, C1. Okay, color of V1 is C1. And now the processing step is color Vi with the lowest unused indexed color. By its neighbors. Yeah. So if, let's say, this is my Vi, and this has some neighbors. And since I said I'm putting some order on it, so these are the neighbors which have appeared earlier, and there could be some other neighbors which will have, let's say, some Vi plus epsilon, Vi plus epsilon prime, some higher values. But these are the neighbors, and each neighbor, since it has come before Vi, everyone would have got some color. Let's say Vi1, Ci2, Ci3, and Cil, let's say. Out of these, since these are here, you're seeing them I1, I2, IL, but these are all numbers. So whatever is the lowest number which is unused, you put that color to this vertex. Okay, so this is nothing but, so this set where you have to check for the colors is the vertices up till Vi and take its intersection with the neighbors of Vi. And whatever is the least used, you use that color on the Vi. This way, what you would have done is, I think third, 2 bounds we have seen already, that the chromatic number of G is less than equal to maximum degree of any vertex plus 1. This delta G means maximum of degree of V in vertex set. Degree meaning how many neighbors it has. So maximum degree plus 1, because whenever I'm standing here, what is the worst case scenario? That all of these vertices have appeared with different colors. So I have nothing left. And this is the vertex of highest degree, which means this is delta G. And then since all the colors have been used, I have to put the new color to this vertex. So delta G plus 1. But within this bound, chi G is done. Okay. So chi G cannot exceed this. But this is a really, really bad bound. And quite expected because, greedy algorithm, as naively as we have applied, is never bound to give good results. A better result which one can improve to is this, that if you take, let's say, the degree sequence now is, let's say this is the highest degree I'm putting as D1. Okay, so whatever okay, so all the n vertices, every vertex has some degree. Arrange the degrees in the non-increasing order. And this degree sequence, if you follow, then chromatic number of the graph is bounded from above by 1 plus max over I of minimum of di or I minus 1. So you can see that this being the highest degree also is going to give you at max this answer. So this is a refinement of the bound 3. But still, it's not very good. And also, the ordering is quite important. For example, I guess example 7. If let's say I look at this and I say 1, 2, this is my labeling for the vertices. Then, as per my algorithm, I say put one first color to the first available vertex. Now you come to the second vertex. Choose the lowest non-used indexed color. It's C2. Put C2. Come to C3. So for C3, for the third vertex, C2 has been used by its neighbor, but C1 is available. So I'm going to put C1 to it. I come back to C4 for the fourth vertex. Again, C2 has been used. I'll put C1. I come to fifth vertex, and by its neighbors, C1 has been used, which means C2 is available. I will give C2, which means I have used 2 colors. Now, if I will, let's say, used 2 colors. If I choose the same graph, exactly the same, but now I change the labeling of the vertices. What do I do now? I say this is going to be my first vertex, but now this is my second, third, fourth, and this is my fifth. Then again, this gets C1. Now we come to C2, and C1 is available because its neighbors hasn't used anything. So you give it C1. You come to C3, this gets C2. You could come to this gets C2. Now you come to 5. 5's neighbor has used C1 and they have used C2 as well, which means this has to be given C3. So now I have actually used 3 colors. Just a moment. Yes. So the way I'm labeling the vertices is making a lot of difference. The same graph and quite small, not even a huge graph. And you see, I have used extra colors. So one has to figure out a way where I can order the vertices in a nicer way. And to do that, or rather when I can say that things match up, is through a concept called interval graph. These are graphs which are constructed from the intervals. So suppose we have a family of intervals. Let's say some intervals like these. Okay. 2, 3, 4, 5, 6. I have 6 intervals. So what do I do? From these intervals, I construct a graph. How do I construct? I first of all put one vertex for each interval. So I have 6 intervals here. And now I put edges on those vertices, in between those vertices, whose corresponding intervals have an overlapping. So you see, 1 and 2 do not overlap, which means 1 and 2 are not going to be adjacent. 1 and 3, yes. So if let's say I draw a line like this, I can see 1, 3, and 5. They are overlapping, which means 1 has to be adjacent to 3, 3 has to be adjacent to 5, 1 has to be adjacent to 5. Similarly, 1, 3, 6 are also adjacenting, overlapping. So this is also there. 2, 3, 6 is also there. 2, 4, 6 is also there. Anything left? No. So this is a graph which corresponds to the intervals which were given to me. And with this, I have my next result. Which says that if G is an interval graph, then the chromatic number of G is exactly equal to the click size. Chromatic number cannot be larger than the click size. And why, even though the greedy algorithm is having defects that depending on the labeling, I'm getting different answers and all, because scenarios, using it helps us prove results. And this is one such scenario. So here we can use greedy algorithm, provided we make a good choice of the vertices. Okay. So maybe proof I'll skip. We'll see if I can come back to this. But coming back to Sachidanand's question, remember in the beginning, I said that chi-g is at least 1 plus the max degree of the graph. And I said that equality holds if G is equal to Kn, the complete graph. Maybe I can leave this place so I can come back. So this is the last topic. So what we saw earlier was that chromatic number of G is at most 1 plus the maximum degree of G. Remember, this was the max of all the degrees. And we saw that if the graph happens to be Kn or an odd cycle, Cn denotes a cycle of length n, C2n plus 1 just means it's an odd cycle. So if I have G to be Kn, max degree is for any vertex is n minus 1. If you, let's say, see this, if you look at this vertex, it has this as a neighbor and this as a neighbor, two neighbors. Other than itself, it is adjacent to everything else. So it has n minus 1 neighbors. So n minus 1 plus 1. N, which is the chromatic number, so equality holds. If you look at any odd cycle, this is also an odd cycle, by the way. But here, any odd cycle, and the max degree or degree of any vertex is 2 plus 1, which is the chromatic number. Any odd cycle needs 3 colors to be colored, to properly color it. So this we had seen. What Brook's theorem tells us is that these are indeed the only graphs for which the equality will hold. So what it says is that chi g is strictly less than 1 plus delta g if g is not equal to kn or c2n plus 1. Well, why do I care about such a result? So, a very a quick way to look at this would be if I, let's say, give you an example of a graph which looks like this. So people who have seen graph theory will be able to recognize this very quickly as Peterson's graph. Okay, so clearly this is not just a cycle. So let's say if I short it as pet, then pet is not equal to C2n plus 1 for any n. Also, it's not a complete graph. For example, this edge is absent. Okay. So this tells me that the chromatic number of G is strictly less than 1 plus delta G. Now you look at delta G. If I look at any vertex, every vertex has 3 neighbors, which means delta of pet is 3. This implies the Brook's theorem that the chromatic number of pet is less than 1 plus 3, or rather less than equal to 3. And since it has odd cycles, 1, 2, let me. This has odd cycle. You can see this itself. So this needs at least 3 colors for sure, which means so chromatic number of Peterson's graph is equal to 3 without even looking for any explicit coloring of it. So this is why Brook's theorem is important. And with this, I'll take a pause. if I have like 10 seconds, I can quickly give a proof of this particular result. Let me know.
Yeah, please go ahead.
Yeah. So coming back to this, recall G was an interval graph where every interval was represented by a vertex and the overlapping intervals were made adjacent in the graph. Now, I have to say that the chromatic number is exactly equal to the clique size. I will apply GD seven and example 8. This is an extremely strong tool. And proof goes like this. Let's say, so first of all, what do? I have to give an ordering to the vertices of this interval graph. I give ordering to the vertices according to the left. So whichever intervals have lowest endpoint gets the indexing in the ordering. Okay. And now you apply the greedy algorithm. When you apply the greedy algorithm, what happens is, suppose V is a vertex in your interval graph IG, which receives the value K. Okay. And K is the maximum color that is assigned through this algorithm. If this is the case, so what am I saying really is that color of V is K. And if I let V to look, denote the interval XV, YV, what are we really saying? That the color 1 all the way through K minus 1 were used on earlier neighbors of V. Remember the greedy algorithm? The lowest index color which is not used on its earlier neighbors, that color you give to the current vertex. So if V is getting the color K and that is the maximum color, then this means 1 through K minus 1 all have been used on the neighbors of V, which have appeared before V. So these are used on earlier neighbors of V. This means this endpoint has been there in all of these intervals, or rather this full interval has intersected these many intervals, correct? So XV belongs to each of these neighbors is an interval, right? So these belongs to all of these intervals, these intervals. And this, if I would say that you take the interval V along with these intervals, sorry, these are how many intervals? 1 through K minus 1. So K minus 1 intervals, along with one more interval, they will form a k clique or a clique of size k. So the clique size of the graph, which could be actually bigger than k, because I have found one clique of size k. The clique of the graph could be bigger than this. But now this is less than equal to chi g, because I said k is the maximum color which this greedy algorithm has given to this vertex. So I have omega g is greater than equal to chi g. But very trivially, we have seen that chi g is at least as much as the omega g, because every click, uh, every vertex of the click gets different colors. So chi g is equal to omega g in case of interval graphs. But you have to make a careful choice for using the greedy algorithm. And this ends the proof. Now we are open to questions.
Yeah,
Am I
Bhumika.
audible?
Yes. Thank you, ma'am. Now I will any questions they have. You can write the queries in the text box, or you can use the raise feature. For those who are watching it live on YouTube, you can write your question in the chat box. We'll make sure that your question will reach the speaker.
Yeah, Sachidanand.
Yeah. I have two questions. The
Yeah.
first question regarding the inequality again. So basically, this interval graph is again an example where we have an equality.
Yeah.
But I'm asking, for example, in the Brook's theorem,
Mhm.
it says that we have an equality for the chromatic number and the 1 plus the maximum degree, if and only for these two graphs. So do we have such equality for the chromatic number and either for independence number or clique number?
This is a question you had earlier asked, right? For the bound 3?
Sorry?
Which bound you're talking about right now?
Oh, so basically the inequality that the chromatic number is less than equals to the omega g.
This one.
Yeah, sorry, greater than equals to, yeah. So basically here we saw that for Kn we have an equality, and just now you also told for this interval graph we have an equality.
Mm-hmm.
Now I'm asking as per like Brook's theorem, we have a chromatic number of G equals to 1
Oh, you're
plus
asking if there is a characterization for equality of this bound.
yeah, either
which
this bound or the
graphs?
second bound.
Second bound is hardly used.
Yeah, second bound is of course not that much useful, but the first bound is useful. So that's why I'm asking if
Yeah,
there
I'm
is
not
an
sure if
like
there is a full characterization of for which graphs this is equality, and for anything outside this class, it would be a strict inequality. I don't think that is true.
okay.
Yeah.
And the other question is regarding this. If you go to the Cartesian product,
Mm-hmm.
of, so basically the Cartesian product of two path graph is a grid graph.
Yes.
So now if we talk about the independent set, so for
Mm-hmm.
the path graph we know what are the independent set.
Right.
So so can we describe the independent set from this? Why I'm asking this, because there is something called independence complex which can be derived from the independence set,
Mm-hmm.
and for the grid graph it's not completely solved. So
It
that's why I'm
is.
interested if
It is solved.
but it was, I guess Anurag's paper was, he told that it's wrong. So that's why I'm telling.
Well, matching complexes for the grid graphs have not been solved, but the independence complexes have completely been solved. And if I'm not wrong, it's
For the
stated by
grid graphs?
Matsushita. Yeah. Last year it was
Oh,
solved.
it's a recent paper?
23. 23, yeah.
Oh, okay. Oh, so then I
It
missed
has been
the recent paper.
completely settled.
Okay.
Yeah, the matching complexes are done only for up till 3 cross n. That is, I mean, that's a paper where I am also a co-author along with Anurag and Samir Shukla. That one we have
Yeah.
done the maxes. 4 cross n, I have results, but they are not solidified, so I will not say anything. But the independence complex have been completely settled.
Okay. So this I was not
These
knowing,
are
because
again
the
wedge of
recent,
spheres.
yeah, the
Yeah.
wedge of spheres is basically, yeah, okay.
It
No,
came
because the
before
recent result
the
I
June.
was knowing is like n cross 6. Okay. So
No,
that
I
is
think
for
it's
the square grid
Matsushita's
or
paper.
any m cross n grid?
No, when we say square grids, we are meaning n cross n only. N cross m.
No, I'm saying that it's m cross n grid or n cross n grid.
P cross q works.
Oh, so for any
Yeah.
grid. Okay. Ah, I see. Okay. Yeah, okay, thanks.
Any other questions?
Your internet connection is
So Matsuda's, that's why I was talking about. So I was knowing Matsuda result for n cross 6 grid. So I was not knowing for arbitrary.
Yeah, I'm also looking at that.
Because the recent result I was knowing about, like recently n cross 4 and n cross 5 came, that I was knowing, and n cross 6 I had read last year when he posted on archive.
Goyal has left
But
the
I was not
meeting.
knowing if
Shuchita
n
Goyal
cross
has
m
joined
has
the
been solved,
speaker
because
queue.
I asked
Goyal has
Anurag this
joined the
question
meeting.
like maybe a year ago, and he told that he was having some result that, but later he found that was not correct. So that's why he removed from archive, I guess.
Yeah, there was some issue in his but that was about the matching complex, not the independence complex, if I'm not sure.
Okay.
I mean, there is some confusion, but one particular graph complex got solved for the grid graphs completely for all indices.
Okay.
If you drop me an email, or if I can get your
Mhm.
email ID through one of the organizers, I will write back to you with more details.
Yeah, okay, sure.
Yeah. Mhm.
But is there any characterization for, let's say, if I have G a graph and H be any other graph, and if I know the independent set of G and independent set of H, so is there any way, or like that we can determine the independent set of G Cartesian H?
Well, that's what Anurag had tried doing in his paper, and that had fault.
Okay.
So is that paper not available on archive anymore?
I haven't checked afterwards. I talked to him, I guess, maybe 1.5 years ago. So,
Yeah, I think he uploaded it back in 2022.
okay.
Oh, this has been retracted. Okay. Yeah, there was
Yeah, he only
error in
told
the
that he
proof.
removed that. So,
Yeah. And that, I mean, the idea of the proof was that he was trying to construct the independence set of the Cartesian product of the graph using the independent sets of the individual parts.
mhm.
And that construction was wrong.
I see. Okay. Yeah. Okay, thank you.
Yeah, any other question?
I also have another question that's like related to graph, but that's like, so do you know this? There is something called zero divisor graph.
Okay.
So that's basically formed with if you have a ring, and if you
Mm-hmm.
consider the zero divisors, non-zero zero divisors of that ring, then there is an edge between two vertices if and only if their product is zero.
Okay.
So this is called the zero divisor graph, and so they are basically because I was interested in finding out the chromatic number, and also I was that's why I asked this, because I'm getting a graph G and H, and I wanted to find some relation of the independence set of the Cartesian product of G and H with the zero divisor. So that's why I asked if there is any relation between the independent set of G H and the independent set of G Cartesian H. So yeah. So if you get any
I will have to look at the zero divisor graphs.
okay. No, like mainly this result. If you get any maybe reference or something regarding this result,
For the
that
independence complex?
no, the independent set of G H and the independent set of G Cartesian H.
Okay.
If there is any relation, such relation, because I did not able to find it out. So
Sure, I'll try to look it up.
yeah, sure. Thank you.
Yeah. Hmm.
So, since nobody has questions, I thank all of you to be be a part of this lecture.
Bhumika,
A big shout out.
Sanjay raised hand. Probably. Sanjay
Okay.
raised. Sanjay, you wanted to say something?
Hmm.
No, I guess.
No. Okay, Bhumika, carry on.
So a big shout out to you, ma'am, for explaining it in such a wonderful way. Thank you so much for explaining to all of us graph theory is so beautiful and you made it more beautiful. Thank you, MTTS. Thank you, Soumya De sir, and everyone. Now I request everybody to turn on their camera so we can have a glimpse of this lecture.
I'm also very thankful to MTTS. The only reason I am in maths today is the MTTS.
Bhumika, you are muted.
Okay, so I'll count down till 3 and then I'll click a picture. So I hope everybody has done that. Or should I wait for a while? Okay, so 1, 2, 3. Okay, thank you. Now please feel free to leave the meeting.